Hello, this is the first problem of section 8.3.1 after the opener. So we are given a polynomial. This is a third degree polynomial based on the degree of the leading term. This is a third degree polynomial. And we are starting with the idea that if we look at a graph of this, we can see one real root. And again, all odd degree polynomials would have at least one real root. The graph was given to you also in a graphing calculator. If you actually graph this function, it would look like this. This is a cubic, and we can clearly see that there is an integer value at which it passes through the x-axis right here at the value of x equals 2. I scaled my x-axis by 1 unit, and so we see that there's a fractional and another fractional or even irrational root, but we can't figure out what those are. But we do see an x value of 2, and that's what was given to us in this problem, is that we can see that there is a root. We see a root graphically at x equals 2. And they also ask us to verify that this indeed is a root. And how we would verify that would be to check, right? We would verify by checking if you plug in 2 anywhere you see an x, do you really get out 0? Because again, that would be the definition of if it's a root or not. And so if I did that checking, f of 2 would equal 2 cubed plus 2 times 2 squared minus 7 times 2 minus 2. Now simplifying this is the same thing as 8 plus 8 minus 14 minus 2. And I hope that you can see the 8 and the 8, that would add to 16, and then the negative 14 and the negative 2, negative 16. So this does, in fact, equal 0. Therefore, this is really a root. Now, since that is a root, right, we know that since x equals 2 is a real root, what this means is that x minus 2 is a linear factor of f of x. And we know that it's a linear factor of f of x because, again, using kind of zero product property backwards, if I would subtract 2 and set that equal to 0, that must have been how I could, for example, have got that real integer value out. So once we do that, we can actually use this concept to figure out, well, how do we factor this third degree polynomial? And so we are going to build on our understanding of using a rectangular area model in this lesson, in addition to also going through long division process. So now I have to think about, if I am going to divide a third degree polynomial by a linear factor, what degree polynomial would I have left? So again, if I took a third degree polynomial, f of x, right? This was a third degree polynomial, and I divided it by a linear factor here. What degree polynomial would I have left if I had an x cubed up here, right, and an x here? I would end up with an x squared like polynomial. So this is going to result in me having a quadratic, right? And so this would be a second degree polynomial would remain. So a second degree polynomial would remain, and they could have up to 3 terms, right? Here's the first term, the second term, and the third term. It may not have all of those, but it's definitely going to at least have an ax squared term. Now, all of that information helps me to set up an area model. So I use this concept that I know that the sum of my parts inside the area model have to be this cubic, right? So the sum of what's inside is going to end up being x cubed plus 2x squared minus 7x minus 2. And I'm going to divide it by the linear factor x minus 2. And so I label the outside of a rectangular area model with that linear factor that only has 2 terms. And then since I know that this is going to end up with a resulting x squared polynomial on the top, I actually know that that has up to 3 terms, and that dictates how many columns I make. So again, what goes in the first now cell will be the x cubed, and that comes from the sum, right, of what's going to be the sum of all these things inside. And now here goes on how you actually complete an area model method of factoring a higher degree polynomial. So I have to think about if this dimension right here is x, and I know the area inside is x cubed, then the top dimension must be x squared. Because again, x squared times x is x cubed, and this represents the area of the dimensions of the rectangle. So now that I know that this is x squared, now I'm going to take and multiply this x squared times a negative 2 and write what I have left. I've got a negative 2x squared. Now I have to think about, I know that the sum of what's inside of this rectangular area model must equal this whole thing. So that means that this term here is going to combine with another term. And that term, the sum of it has to end up being the positive 2x squared. So what do you add to a negative 2x squared to get a positive 2x squared? 4x squared. So again, 4x squared plus that negative 2x squared would combine to be that term that I need inside. And so I'll use a different color now to say, okay, well then that means up here, if this side is x, I must be adding then 4x, because 4x times x is the area of 4x squared. And now I take and I multiply that 4x times the negative 2 to get a negative 8x. And likewise, I know that that's going to have to combine with another term in the rectangular area model that makes it a negative 7x. So what do I add to a negative 8x to get it to be a negative 7x? Just a 1x. And if this is 1x and that dimension is x, then I must be, in this case, adding a 1. So here I'll write plus 1, and 1 times the x is the 1x, and 1 times the negative 2, well, that is negative 2. And so notice that these two match, okay? So these two match. They're the same. Therefore, the remainder here, the remainder is 0. And I knew that the remainder should be 0 because earlier I had checked, is f of 2 0? That means that your polynomial is divisible by this linear factor x minus 2. And this is similar to the concept of doing long division. If you have a 0 remainder, it really means that whatever you were dividing, it was divisible by that factor. I'm going to show the same process of now completing the same idea using a long division. So how would we set up the same process but doing long division? Now our Integrated Math 3 book published by CPM actually highlights this strategy, which I really love, this area model strategy. The area model strategy builds on your guys' prior understanding of how you multiply binomials. However, there's also been a long time where we've actually used long division to do this. So I want to show both methods because it's important to know that you can sometimes use one method or another method, and in higher level mathematics, they might expect you to know how to do long division. So if you would like to continue watching the video, I will go through how would I, in this case, do the same problem, but using long division. Well, again, I know that the polynomial that I am going to be dividing is x cubed plus 2x squared minus 7x minus 2. Notice every single term as you descend down, there is an x to the third, x squared, x to the first, and then like technically an x to the 0th. What that really means though is that I don't have to have any placeholders, like for a 0 coefficient. So I put my long division bar there, and again I'm going to do the same idea. I know that this third degree polynomial is divisible by x minus 2, so I put that in the front, just like we do when we do long divisions of numbers. And then I start this problem the same way. I think, how many times does this x go into x cubed? Well, it goes in x squared times. And I know with long division, you know that then you multiply, for example, the number that it goes into by this other number. Well, this now is an actual variable. So now I have x squared, And then I also have to multiply it by that -2. And so then right here, I write minus 2x squared. Then, just like we always do, we subtract, right? After we multiply it through, then we think, okay, well, what is that product, right? And then we subtract it. Now, you have to be very careful here. One thing is that I just noticed that I just wrote x squared times x. That would be x cubed. And then again, here we've got the -2x squared. So now I'm going to be subtracting these. Well, that's the 0 that I was hoping for. There are 0 x cubes left. But here, this negative applies to that negative. So this is saying 2x squared minus a -2x squared. That actually results in a 4x squared. Now remember, the next step, whenever we were doing long division, was to bring down the next number. So we're going to do that now. We're going to bring down that -7x. So then we have a -7x. And now I have to think, how many times does this x go into 4x squareds? Well, that goes in plus 4x times. And then I repeat this whole idea. 4x times x is 4x squared. 4x times -2 is -8x. Then again, we subtract, because that's always what we do with long division, but we've got to subtract everything, so I always use parentheses, because again, this negative will apply to that next term. It's a common place of error. So now again, the 4x minus the 4x squared, that's the 0x squared that I expected. But then, now we've got the -7x, right? And then minus a -8x. -7x minus a -8, that would just be plus a 1x. And now finally I got to bring down that last -2 and think about, again, how many times does this x go into there? Well, it goes in 1 time, so plus 1. And now again, 1 times x is 1x. 1 times -2 is -2, and look, those two match. So therefore, you're going to have a 0 remainder. So remainder is 0, and that is, again, the same quadratic that I got from the previous method. Now, what does this mean? It really means that for both of these problems, I could have rewritten f of x. It's the same thing as the linear factor x minus 2 times x squared plus 4x plus 1. And if I were expected to find the remaining factors of this, or sorry, the remaining zeros of this, I would use this quadratic factor, which is not factorable. So I would have to use quadratic formula or complete the square to find the remaining zeros. So again, the remaining zeros, we find them. When does this equal 0? Well, again, we could say, well, it's when x squared plus 4x plus something equals -1 plus that something. And completing the square, half the middle term squared is 4. Half the middle term squared, again, gets added to the other side. Rewriting it as a perfect square trinomial, we got x plus 2 quantity squared equals 3. Taking the square root of both sides, taking out the absolute value, I would get a final answer of, again, -2 plus or minus the square root of 3. And so those are my other real roots, but they are irrational roots. And that is, again, why we could only see the root that corresponded to the x equals 2 graphically. But these other roots are there, and once I learn how to divide polynomials, I can start to finally figure out from standard form what all of the factors and zeros of all higher order polynomials are.